In today's video, we will be solving LeetCode's 981 medium difficulty problem. It's called time-based key value store. So let's start with reading the description. I also added the description here in the comment section. So yeah, let's go through it. So we need to design a time-based key value data structure that can store multiple values for the same key at different timestamps and retrieve the key's value at a certain timestamp. Basically, we need to create and implement a variation of a hash map that would deal with timestamps as well. So anytime we add a value to the hash map, we are adding not only the value for a given key, but also a corresponding timestamp when the value is added. So we basically need to implement the time map class. The time map class contains the constructor, which initializes the object of the data structure. And also there are two methods which we need to implement. One is called set, which is used to store values with corresponding timestamps for a given key, and also get, which would retrieve the value for a given key, but also for a given timestamp as well, and the result would be the value would be actually a string. So here we are dealing with a kind of a simplified map that uses strings as both keys and values. So the values are strings, and yeah, that's why here the get method returns a string, and also the set method consumes a string value as a for the value attribute. So get method returns a value such that set was called previously with timestamp less or equal than timestamps. If there are multiple such values, it returns the value associated with the largest timestamp prev value. If there are no values, it returns an empty string. So this might seem a little bit confusing. So let's switch to an example, and here we have an example pairs of inputs and corresponding outputs. So let's see. First, it's called with a set with the key foo and the value bar and the timestamp 2. The output is null because set is a void method, therefore returns no. There's no return value here. Then, so at this point, the map contains a single record for the key foo. The value is bar with the timestamp 2. When get is called with the foo key and the timestamp 1, it returns an empty string. Why? Because the timestamp which was requested here with the get, in the get method is strictly less than 2 with the timestamp when the value was added, and that's why an empty string is returned. But when we call get foo 3, because 3 is greater than or equal than 2, in this case it's strictly greater, the bar value is returned. But when we call set foo and bar 2, so another value, so this version of the map supports multiple values for a single key. So a key can be resolved to multiple values. So set foo bar 2, but the timestamp 4, and when we call get foo 4, the value that should be returned should be bar 2. So at this point, key foo resolves to two values, basically, bar with the timestamp 2 and bar 2 with the timestamp 4. So given that we call get with foo, which is and timestamp request and timestamp 4, it should return bar 2 value. The same value should be returned when get is called with foo and 5. Bar 2 should be returned because there are multiple values less than 5, 4 and 2, multiple timestamps, but in that case it returns the value associated with the largest timestamp pref. So in this case it's this one, and that's why bar 2 is called again. If we call get foo 2, if we would call get foo 2, in that case, the result should be bar, because 4 is strictly greater than provided value 2, and that's why value bar is returned. And here there are a couple of constraints, and one of them is very important constraint that directly impacts the final solution of the problem. So let's go through the constraints quickly. So both key and value parameters are never null nor empty strings, so they always have a length which is at least size of 1, which is at least 1, but the length of both key and value values is never greater than 100. Key and value consist of lowercase English letters and digits, and timestamp value is an integer which is somewhere between 1 and 107, including 1 and 107. And probably the most important constraint is that all the timestamp offset are strictly increasing. That means when a set method is called multiple times, the timestamp values are strictly increasing. So here it's called, for the first time it was called with the timestamp 2. The second time was called with the timestamp 4, which is greater than 2. That is a very important constraint. And at most 2 times 105 calls will be made to set and get. So this is from the LeetCode description. So this tells us how many times get and set methods will be called during the testing phase, or while after you submit the solution at most. So let's see how we can implement this solution. So here is the time map class, which has the constructor and set and get methods, where set returns no value. It is used to store the value with the timestamp for the given key, and get would return the string value for a given key and the timestamp. So so we know that this will be a kind of a hash map, and maybe it would be nice for you to familiarize with the concept of hash maps, and if if you don't know about hash maps, I would highly recommend reading and getting yourself familiarized with the hash maps. And maybe we can create a separate video where we will be discussing the hash maps only and how they are implemented. But here, the main, I would say, the most important thing about hash maps is that it's a kind of a structure which optimizes get and set functions. So it can really quickly retrieve a value for a given key. So it's a key value structure in the constant time. It should be in constant time. But on the other hand, some other things are not that efficient. For instance, if you would like to find the maximum value in the map, that wouldn't be that sufficient. In that case, some other structures should be used. So HashMap specializes in retrieving a value for a given key in an efficient way, in the constant time. So what kind of hash map we should be using? So it should be a hash map of that would use string as a key, because that's that's mentioned in the description. It should be a map that deals with string keys and string values. But in this particular case, given that a single key can resolve can be resolved to multiple values, so it should not be a string hash map, but string list hash map. We can call it a map. So in this, I'll create the data structure we will be using is a hash map. So in the time map constructor, we will initialize that hash map. So by the way, I will implement the solution in Java programming language, but it should be quite straightforward to implement it in any other, implement the same solution in any other language. So, but here the value is not only string, but it's kind of a pair of string and integer, or string int, where string is the value and int is the timestamp. So we need to create a kind of an inner class which will be called pair, which will actually be the value, the type of the value here in this example. So in Java we can create a private class which will be called pair, and it should be quite a relatively simple class. So it should have private string value and private int timestamp. So let's create a constructor for this pair. So public pair string value int timestamp, and we can say this that value is equal to value, this that timestamp is equal to timestamp. And also, given that these two attributes are private, in order to access them, we can create, so we can either make them public, or we can create getter methods, public getter methods. So let's create get. So in IntelliJ the environment can generate these getters. So get value and get timestamp. So here we have the getters. So that would be the way how to read these two values. We don't need a setter because once we will provide the initial values through the constructor, and those values will never be changed, at least not for this solution today. So here the map that will be used is a map of string to a list of pairs. Okay, it's a list of pairs. So how can we implement these two methods? So let's quickly discuss how can we implement these two. So the set method should be fairly straightforward. If there is a key already present in the map, we should just get the list to the corresponding key and add the new element to the list, new pair element with the provided value and the timestamp. But if there is no such key, that means that we are adding this value for the first time. We will just simply create a new array list and add a new pair with the with the provided value and a timestamp to it, and yeah, add that list, put that list into the map for the provided key. This should be fairly straightforward. However, when retrieving the key, a value for the provided key, how can we implement this? The naive approach would be, we can simply get the list and then linearly iterate through the list for the provided key. But that would work, definitely, but it would have the linear time complexity. So let's see, for instance, if the map is something like this, key is foo, which resolves to the list of value 1 with the timestamp 1, value 2 with the timestamp 2, value 3 with the timestamp 3, and if we call get for the key foo and the timestamp 3, we would need to iterate through the list and find the value 3 or the greatest value less than 3 if exists here. However, there is one important thing to notice here, and then important thing is the constraint number 4, which says that all the timestamps of set are strictly increasing, meaning that if we add, anytime we add a new value, if we add it to the end, this list of values for a given key will have these timestamps strictly increasing. So the first value would have the smallest timestamp, the second value would have a timestamp which is strictly greater than the first one, and the last element would have the greatest, the largest timestamp. So this list will be sorted strictly sorted by timestamp. So anytime we add a new value to the list, we just need to make sure to add the value at the end of the list, and when that would result in the sorted list when retrieving the value. So why is this important? When we need to retrieve the value for a given timestamp, instead of going linearly through this list, we can use the binary search to find to find the result value. And so this naive approach would have the time complexity O of n, where n is the size of the list. But binary search approach would have O of logarithm of n, again where n is the size of the list. So it's better, definitely it's more optimal, and therefore we need to apply the binary search here to find the resulting value. And finally, how can we use the binary search here? How can we modify the binary search approach to find the value? Well, if the list has the following timestamps. So for now, we can forget about values. Let's just focus on the timestamps. 1, 2, 3, 4, 5, 6, 7, 8. And if the requested timestamp is, for instance, 4. So we should return this value, which corresponds to this timestamp. So how can we use the binary search? We basically need to use binary search to find the first element in this list with the value greater than 4. So because it could be the case that there is no 4. So let's say, for instance, okay, let me remove this. The timestamps are 1, 4, 6, 8, 10, 11, 17, and 18, for instance. And let's say if the timestamp is 4 or 5, for instance, here some values will be less or equal than timestamp, and some values will be strictly greater than provided timestamp. So we can divide this list to basically those that are less or equal than the timestamp. So the first one is, so we can say yes. The second one is less or equal than 5, but the third one, no, is not, because 6 is greater than 5, and all remaining timestamps, because this list is sorted, are greater than 5. So what we need to do, we need to find the first element in this list whose value is strictly greater than provided timestamp. So we need to find this one. And the result should be one value before this one, 4. This is how we are going to apply the binary search. So we will basically apply the binary search to find first element greater than the timestamp, and then return, and then we can return the previous element. But there are some edge cases. Which we need to take care of, pay attention to, because it could be the case that all elements are less than the timestamp, or all elements are greater than the timestamp. That's why we need to be careful. Okay, so that should be the solution. Let's start. First, let's try to implement the set method, which is, in my opinion, more straightforward. So here, I mean, we can check whether if key is null or key is empty or value is null or value is empty, or even if the timestamp is less or than or equal than to 0, and we can throw new illegal argument is an exception. Are invalid. Okay, so what we need to do, there are two cases. First one is if the map contains key, and the other branch would be when the map does not contain the key. So if it contains the key, we can say list pair list is equal to map.getKey and what we need to do, we know that this list will never be empty, so we can simply if there is a list in the map, it will never be empty. So we can simply add list.add new pair value and timestamp. But additionally, what we can do here, we can check whether this timestamp is strictly greater than the last previously added value. That way we can ensure that the list is sorted by the timestamp value. So if list dot, so let's find the last element, which is indexed with the size -1 value, that timestamp is greater or equal than the provided timestamp. In that case, we will throw new illegal argument exception. So here we have some constraints, and those constraints probably mean that we can assume that these constraints are always true, and in that case we don't need to make all of these checks. However, if you are applying for a job and if this is an interview question, it might be good to at least let them know that you are aware of these checks, so you can clarify with the interviewer whether you need to implement this or not. They might say, okay, we can assume that the constraints are always true, we can assume and skip these checks depending on the amount of time you have, but it's always good to at least clarify this, because some interviews might pay attention explicitly would like to see explicitly whether you are aware of these edge cases and or these constraints, and they might insist on you to implement them. So that's why I'm adding these checks here. So here, provided timestamp value is not greater than previous added timestamp. Okay, and if this condition is satisfied, we will not enter this branch, but we will simply add a new pair value, a new pair with the provided value and the timestamp. So that's the first case when the map does contain the key. If map does not contain the key, that means that we are adding this value for the first time, so we need to create the list. So list pair list is new array list. So array list is a part of the standard Java, and it basically it's an implementation that that can let us access any element of the structure immediately. I mean, in the constant time, basically like an array. But at the same time, it supports dynamically adding new values. So under the hood, it does it extends the corresponding array. So we don't need to take care of the size of the of the list. So here, when we add a new value, it will be added strictly at the end of the list, and that's why we are using it here. And it's important to use the array list in this case, because we really want this set function to be to execute efficiently in the constant time. So that's why I'm using the array list here. Apologies. So I've created the list, and let's just add the new pair. So list that add new pair value and timestamp. Maybe to make this more readable, we can initialize this pair here. Okay, and we will say map.put for the provided key this newly created list. And that's the end of the set method. So we can quickly analyze the time complexity. So here this executes in the constant time, and here we have two cases, and we said that map resolves a key to the value in constant time. Same applies to this constant contains key method. So this is all constant. Here we get the list for the provided key. This is also in constant time. This is how hash maps work. And yeah, this check also is in constant time. And when we are adding a new value to the list, because we are using the array list, it will always add the value at the end of the list, and it will do it in the constant time. So we can assume that this executes in constant time. However, under the hood, this array list, once it reaches the max, the limits, it may require some extra time to extend the size of the array, but we don't need to think about it for now. We can simplify this and say that this executes in the constant time. And finally, here this block also executes in constant time. So overall, the set function or set method executes in constant time. We can say the time complexity is O of 1. On the other hand, let's implement the get function or method. So first we need to check if it contains this provided key. So if map does not contain the key, if the map does not contain the key, we should return an empty string. Because we will be returning this empty string a couple of times, we can maybe create a constant which will be called an empty string, and it will make the code a bit more readable. String empty string, and we can return it here. Though I think that Java does have some kind of optimization, and it will not create multiple empty strings under the hood. So basically we can also using this expression should be fine. But somehow I prefer creating a constant, because to me it seems more readable when I see return an empty string. Kind of looks nicer to me, but yeah, it's not that important. So if there is no value for the provided key, we can simply return an empty string. I think that was somewhere mentioned in the description. However, if there is a key for the given key, if there is at least one value, we need to check the timestamps. So we will say list pair list is equal to map.get. So for the provided key, it returns the corresponding list of pairs. So what we need to do, we need to apply the binary search to find the first value strictly greater than the timestamp. So how we're going to do this? So we can say that left bound is 0, int right bound is the last element, and we can say while L is strictly less than R, and we can calculate the medium value as, so technically we can say L plus r divided by 2. However, to avoid overflow, when L and R are integers close to the maximum value, a better way to write the same expression would be m is equal to L plus R minus L divided by 2. So something like that. It's a minor optimization, but yeah, it's good to know, and it's always better to write this expression this way. And finally, let's check. So we are now looking for the first value which is strictly greater than the provided timestamp. So it should be, we can say something like this: if the medium value timestamp is greater than the timestamp, so the medium value is strictly greater, that means that this is a good candidate. This is a candidate to be the first value. So we need to find the first value greater. If timestamp is 5, we need to find the first value greater than 5, which is 6. But if medium is, for instance, 10, it's a candidate, but then we need to see if there is a better candidate, which is in the left half of the array. So that's why we need to keep this value. So R is M and not M minus 1. But if this is not true, we can say that L is equal to M plus 1. And at the end of this while loop, the value, if exists, will be in the index L. Okay. So there are a couple of edge cases here. So it could be the case, let's say that the timestamp is 5. So it could be the case that all values are greater than the timestamp. Let's say that the timestamps are 10, 11, 12, 13, 14, something like this. L should be 10 in this case, right? That means that all values are strictly greater. In this case, then L will be 0, and we need to return the value for that corresponds to this timestamp 10. So in that case, we can say if list.get L the timestamp is less or equal than the timestamp, provided timestamp. In that case, we will simply return that value, list.get of L dot value. Another edge case is when all values are let me just think if I this correctly. Sorry, this is when all values are less than, so something like this, 3, 4. Then L will be 4. I apologize for this. And in this case, we need to return this value. But in other case, when all values are greater, will be here, will be 0, and that means that there is no such value that satisfy this condition. That means that all values were added after this timestamp, and in this case we need to return an empty string if L is 0. So L will be 0 in this case. So if L is 0, we will return an empty string. So those are the edge cases. And finally, I'll come back to this one. Let's just finish the implementation. When values are somewhere in between 1, 2, 3, 4, 5, 6, 7, and when the timestamp is 5, L will be first value greater than 5, which is 6, right? So we just need because the list is sorted, we just need to return the value for the L minus 1. So in this case, we will just return list.get of L minus 1 dot value. So here it's important to notice that when applying the binary search, we are looking for the first value which is greater than the timestamp. And it will be stored in the index L. But there are some edge cases. When all values are less than the timestamp or equal, so even here if it was 5, L will be the rightmost value, and we need to return that value. That means that there is no such value, there is no such timestamp which is strictly greater than the provided timestamp. In that case, we return the L value or the last value, whatever. If all are greater, strictly greater, L will be 0, and this is the check. In that case, there is no valid value, so we return an empty string. And finally, if the timestamp is somewhere in between, like here, L will be the first element greater than 5, and in that case we need to return the value for the previous element. So that way we cover all the edge cases. So this should be the implementation. And let's quickly go and test this with an example. So let's create a time map. Time map is equal to new time map. And we can say something like time map dot set foo var, and we can say 1, and we can say something like that, system out println time map dot get foo for the timestamp 1. We can say result something like this. So in this case, the result is bar, which is expected. But if I would call timemap.get, but for the timestamp, okay, for the if I add it with the timestamp 2, and if I call this, the result is empty, because we are requesting for the timestamp 1, which is strictly less than 2. But let's do something like this. let's add foo bar with timestamp 1, and then let's add foo bar 2 value with the timestamp 4, and when we call foo key for the foo key foo and the timestamp 1, the result should be still bar. Okay, but if we do the same but with the timestamp 4, it should be bar 2, as you can see here. And the same should be for any timestamp greater than for timestamp 100. It should still be bar 2. Okay, so this seems to be working fine. So finally, let's just cover the time complexity of the get function. So as you see here, we apply the binary search, which means that every time, in every iteration of this while loop, we roughly get rid of the half of the array, meaning that the time complexity of the get function will be the time complexity to get the list, to resolve this key to the list, which is equal O, which is the constant time complexity. So this is to get the list for the key, which is done here, plus to iterate through the list to find the value using binary search. It should be O of logarithm of size of the list. So it depends on the size of the list. Let's say that the maximum size, if the maximum size of the list, if the maximum size of any list in the map is n, then the time complexity of the get function will be O of 1 plus O of log of n, which is equal to O of log of n, because this function grows faster than the constant function. This constant function does not grow at all, and this grows faster than this. That's why the total time complexity of the get method is O of logarithm of n. I hope you like this, and if you have any question, please feel free to post in the comment section, and I'll see you in the next video. Thank you.